Hello and welcome to the order of reaction video. Today's chemistry topic is Introduction to Rate Law. This video can be useful for both AP and A-level chemistry students, which introduces how to experimentally determine the rate law, including the reaction order of each reactant, the overall order of the reaction, and the value of K with units. Now, experimental methods can be used to monitor the amounts of reactants and or products of a reaction and to determine the rate of the reaction. The rate law expresses the rate of a reaction as proportional to the concentration of each reactant raised to a power. We can see it's M and N. The power of each reactant in the rate law is the order of reaction with respect to each reactant, and the sum of the powers of the reactant reactions in the rate law is the overall order of the reaction. The proportionality constant in the rate law is called the rate constant. The value of this constant is temperature dependent, and the units reflect the overall reaction order. Comparing initial rates of a reaction is a method to determine the order with respect to each reactant. Now, if you take this general equation A plus B, which is giving you C plus T, we can write the rate law for this reaction as rate equals K times the concentration of A raised to a power M times the concentration of B raised to power N. The rate can be represented the rate of disappearance of reactant, and you can see the unit is given to you as well. The rate can represent the rate of disappearance as mentioned, is reported the units of molarity divided by time. And when we talk about A-level chemistry, we say moles per decimeter cube and second inverse. And when we just do AP chemistry, what happens? They just mention the concentration in liters, volume in liters. Now, K is the rate constant. It is specific to this particular reaction, and it is also temperature specific. The A and B are the concentration of each of one of the those reactants in terms of molarity, and M and N represents the order, which you can see that thing it can be 0, 1, or 2. The overall reaction is the sum of the order with respect to each other. So M plus N would lead to the overall reaction order, and you can see that thing this overall order reaction is the sum of the orders with respect to each reactant. The units of rate constant can be determined by looking at the rate law, which we will have a look a little bit later. But if you see some of the graphs, if you can see that thing, there's a graph here which is x-axis. We have concentration of A, and we have 0, 1, and 2 reaction over here. And then you can see that thing this is telling you for zero order reaction, it has no effect on the rate of reaction. So K and A power 0, that concentration of A power 0, and we know that thing anything power 0 is equal to 1, which is equal to K. So K multiplied by 1 is K. So zero order reaction. And if we can the first order reaction, which is a straight line over here on this one, we can say it is directly proportional. One thing increases, second thing increases, or the vice versa. And the third one we can see second order reaction, it is proportional to the concentration of A squared. So that's some of the representation we have got here. If we go further, just trying to identify the graphs here, I have given you this graph here. If you can see, it contains all A, B, C, D, and let's identify which one is which one in terms of order of reaction. So if you say the curve here, I would say it shows the rate decreasing as the concentration increases. This does not represent the usual 0 first or second order reaction. So it means we can say that thing in this case it is, if we can see here, A is over here, the flat line here, it is 0 order reaction, and B is telling you in that case it although stays a straight line, but it's negative gradient, means the rate decreases as concentration increases. So this is not a first order relationship. C, the line, if we can see, C is the one, is a first order reaction, because straight line through the origin tells that it is directly proportional to the concentration. So if we double the concentration, the rate doubles as well. D1, if we can see here, and that represents the second order reaction. Here is rate proportional to the square of the concentration. So doubling the concentration would increase the rate by a factor of 4. So if we can see, these are more explanation. Of course, you can see this table. That's key takeaways from the table. We can see how it links to your rate law and relationship with concentration. Now, this also have made it easy when we talk about the units of K, that it can always be determined by plugging initial concentration and rates with units into the rate law and solving for K. So if you keep your units on your numbers, you should always be able to determine the units of K. I mean, what I would say, how the rate changes as concentration changes, this relationship always help us to determine the order of a reaction. And what I would say to you guys, you need to make sure you don't have to learn these things. You always have to try to work it out, one of the any of the units for K whenever it is needed. Let's say if I have done one thing for you, if we have seen this is rate is equal to Ka square, and in that case we know if we want to find K, we make K as a subject, and of course rate over concentration of A square, and what we know, the mole per decimeter cube per second. This is a rate unit we have got. We just plug in here, and if we want to get the square of this one, we get mole square and decimeter minus 6. And once we just substitute the value in this one, and you can see that thing how we can cancel mole to mole, and of course decimeter minus 3 to 6, and we get the answer eventually in the end, decimeter cube, mole inverse and second inverse. So that's the way we can get the units of this here. And now let's take an example. Here we have the reaction between nitrogen monoxide and oxygen gas to produce nitrogen dioxide. A rate study of this reaction given the data recorded in this table, you can see. We want to determine the order of the reaction with respect to which of the following, NO and O2. Then we have to find the expression of the rate law, and you can see we have to find the value of the rate constant. So these three questions we need to find out from here. And let's try number 1A here. And what you can see here, we're going to determine the order of reaction with respect to each of the reactants. So we want to look at the data, and we want to find two experiments where if I want to start with the nitrogen monoxide here, then I want to find the two experiments where the concentration of O2 remains constant, and the concentration of the NO changes. So if you see, if I put here like this one, so you can see, if I go back to see here, if I put here, now you can see this is constant and where this is changing. So you can easily see that I think the initial concentration of nitrogen monoxide increased by a factor of 3, so 0.02, 0.06, and I can see its effect on the rate as well, which you'll see on the last column. The rate also increased by the factor of actually 9, if you can just calculate from the calculator, or 3 square. So when the initial concentration monoxide is tripled from experiment number 1 to 3, while the concentration of oxygen remains constant, which I just labeled with the pink color box here, the rate increased by a factor of 9, which is 3 squared. Therefore, we can say this is a second order reaction with respect to the nitrogen monoxide. So we get this answer for second order. Now, if we go to the figure out the order of reaction with respect to the oxygen, what we do, I'm going to look at the two experiments again where the nitrogen monoxide concentration does not change and the oxygen concentration does change. So here, if you see, I blocked this one. If we can see here, it is similar and it is basically changing. So it is triple in these two experiments where the nitrogen monoxide remains constant here, and I see also the rate changes. It also getting tripled in that case if we calculate. So in this case, my reaction is the first order with respect to oxygen here, and I am getting that one as first order reaction. So if I want to write down the equation, we have got NO and O2, so I can definitely write that thing here, the K and O2, and 2 plus 1 is 3. 3 second order plus first order 3 is the total answer for that one, but we have got the answer or the expression of the rate law in that case. Now we need to go to part C as well. If you see part C, here they're asking the value of the rate constant. If you see the how we can mention that thing, every time the reaction proceeds, if you see the equation 2 and 2 here, the 2 moles of NO2 produced. Therefore, NO2 appears what we can say twice as well as overall reaction. So it means the rate of reaction half rate of disappearance of NO2. I'm so sorry. And of course from 2NO to NO2. So it means half means whatever the value I've got here. Let's say I'm taking the first row over here, 8.52 divided by 2, I will get something like 2 4s 2 to the 4 is 4.26. So something I'm getting here. So I need to just plug the value in the equation and find the answer in that case. So how we can get the answer over here. So that's an example we can understand. If we move on to another example, this is this is example if we can see the MCQs. You can read through the question, pause the video, and select your answer choice. We have got A, B, C, D, E. You think about it, do your work, pause this video and try to find the answer. So the initial rate data in the table we can see for the reaction represented, whatever the reaction we have seen that one earlier here as NO2 plus O2 is to NO. Now what is the experimental rate law for the reaction? So here again we need to find experiment where we hold one reactant constant and see how the other reactant changes. If we look at experiment number 1 and 2, we can see the concentration of oxygen is held constant here, right? And the concentration of NO changes. So upon closer inspection we can see that thing. We can see that the concentration of nitrogen monoxide is doubled here and oxygen remains constant in that case. And when we talk about this one, is also getting double. So that means its order, we say the rate also double. Therefore, it's a first order reaction straight away. So I can say that thing here. My answer is first order reaction, and you can read the explanation for that one. When we go for the other one, now if I see next, we can look at how oxygen changes in concentration and how that affects the rate. So if we look at experiment number 2 and 3, so I just try to block this one. 2 and 3. So what is doing, the nitrogen monoxide concentration is constant and the oxygen concentration is changes, all right, over here. If I inspect that a little more precisely, when the initial concentration of oxygen increased by a factor of 4 here, then what is happening, that the rate increases by a factor of 16 in that case. You can calculate, or 4 squared we can say. Therefore, it's second order with respect to oxygen. And my rate law is rate equals K times concentration of NO times concentration of O2, which is raised to power second. We can write things in that way. That is KNO and O2 square. So, I mean, what you should take away from here, the rate law tells us all the information we need to know about the reaction. There are three main parts: the reaction of disappearance of the reactants, the rate constant, which is temperature specific and has particular units, and the concentration of the reactants raised to each power. The overall reaction order is the sum of the orders with respect to each reactant. So these are things you should take away. Good luck. Thank you very much.